NASA unveiled pictures from a new space telescope capturing the deepest images of the universe anyone has ever seen.
Deep in the abyss of space, a revelation unfolded that rattled even the most seasoned astrophysicists. The James Webb Space Telescope, humanity's most advanced eye on the cosmos, pierced the veil of deep space and stumbled upon a discovery that defied the very bedrock of astrophysical understanding. It was not merely a curious find or an intriguing oddity, it was something that by all known laws of physics and cosmology simply should not exist. Webb's instruments captured the light from an object so profoundly incompatible with the established models of the universe that it has forced a re-examination of how space-time and matter truly behave. Before we start, smash the like and subscribe buttons for more updates. The event began with the telescope peering into a distant region of the cosmos, a part of space teeming with the faint glow of the early universe. This was light that had traveled billions of years, emitted not long after the Big Bang itself. Webb's powerful infrared sensors were designed to see the oldest and most distant galaxies, peering so far back in time that it would be like watching the universe awaken from its primordial slumber. In this mission, astronomers expected to catalog some of the earliest galaxies, small and chaotic structures that had just begun to coalesce. But what the telescope uncovered was something entirely different. Against expectations, nestled in the shadows of deep time was an enormous, fully matured galaxy that appeared impossibly ancient and well formed. This galaxy, with its spiral arms and structured core, resembled something that should have only formed after billions of years of cosmic evolution, yet there it was, existing when the universe was less than 400 million years old. According to the standard model of cosmology, that was far too soon for such an organized and massive structure to have emerged. The Webb telescope wasn't just photographing history, it was photographing a paradox. This single image threw theoretical physics into a whirlwind. The early universe was supposed to be a tumultuous place, a chaotic fog of particles and radiation, still cooling, still expanding, still forming the first building blocks of galaxies. Stars in those times were thought to be enormous, short-lived and scattered, forming irregular galaxies that looked nothing like the majestic spirals we see today. But this discovery hinted at a radically accelerated evolutionary process, or perhaps a completely different mechanism of galaxy formation that had never been considered. The implications were immediate and profound. If galaxies like this one were forming at such an early epoch, it meant that the raw materials for complex structures, dust-heavy elements, stable star systems, were present far earlier than thought. That would mean that stellar nucleosynthesis, the process by which stars forge heavy elements, must have been occurring in ways that defy current understanding. Either the first generation of stars lived and died far faster than models predict, or some unknown process accelerated the enrichment of the cosmos. In either case, the foundational theories explaining the sequence and timing of cosmic evolution suddenly stood on shaky ground. Scientists began to consider the extraordinary possibilities. Could dark matter be playing a far more dynamic role in early galaxy formation? Was there something fundamentally flawed in the way redshift is interpreted, leading to miscalculations about the age and distance of these objects? Or was this encounter a signpost pointing toward new physics, perhaps involving modifications to the laws of gravity at large scales, or even the existence of parallel universes bleeding into our own? The mystery deepened when follow-up observations showed that this was not an isolated case. Webb began spotting more galaxies in this early time frame that were too large, too luminous, and too structured to be easily explained. One particularly baffling aspect was a light signature of the galaxy. The telescope spectrograph revealed chemical fingerprints inconsistent with expectations. Instead of pristine hydrogen and helium gas, what the first stars should be made of, there were signs of carbon, oxygen, and even traces of iron. These are elements formed in the hearts of stars and scattered through space in supernovae. For them to be present in such quantities, entire generations of stars would have had to live and die before this galaxy came into existence. That scenario seemed implausible given the time constraints, suggesting either an accelerated timeline of stellar life cycles or an entirely unknown mechanism of elemental formation. Moreover, the galaxy's structure was eerily refined. Its spiral arms were not the disordered swirls of early cosmic flotsam, but graceful, tightly wound features orbiting a luminous core. This kind of structure required more than just time, it required stability, gravity, and interactions over hundreds of millions of years. How then could such order emerge from the cosmic chaos so soon after the birth of time itself. The gravitational scaffolding needed to form such complexity should not have existed, yet the notion that massive black holes, anchors of galactic cores, could have formed and matured this quickly only added to the incredible beyond the galaxy's structure. Its behavior challenged expectations. Its light curve, the pattern of brightness over time, suggested a level of dynamism that had no place in the early universe. There were fluctuations, possible signs of active galactic nuclei, or even quasars, which are powered by supermassive black holes. If such energetic processes were occurring at this stage of the universe, then the conditions for black hole formation and growth must have been entirely different than previously believed. This would require a reassessment of the timeline for the birth of these cosmic titans and the environments that nourish them. The existence of such a galaxy also had far-reaching implications for the formation of planets and, by extension, the potential for early life. If galaxies were forming this fast and with such rich chemical diversity, then the building blocks for planets, rocky elements, water-carbon compounds, may have been present billions of years earlier than expected. That dramatically extends the potential window for the emergence of life in the universe. While Earth is only about 4.5 billion years old, this find suggests that habitable conditions might have existed in other galaxies when our planet was still a twinkle in the cosmic eye. The precision and clarity of the Webb telescope allowed this galaxy to be studied in unprecedented detail. Its resolution was such that individual star-forming regions could be mapped and gas flows within the galactic arms could be traced. These observations offered a glimpse not just into a mysterious galaxy, but into a radically different version of the early universe, one that was more mature, more active, and far more structured than the standard cosmological narrative had allowed. It was as if Webb had tuned into an alternate history of the universe, revealing a cosmic playbook that diverged wildly from the expected script. What made this encounter even more astonishing was its sheer defiance of statistical probability. If one such galaxy existed, it might be dismissed as an anomaly, but as Webb continued to scan the skies, more of these ancient, impossibly evolved galaxies began to appear. Each new detection added weight to the idea that this was not an exception but part of a hidden chapter in the story of the universe, one that had gone unread until now. This wasn't just a minor edit to existing theories, it was a narrative shift so fundamental that it threatened to render large swaths of astrophysical literature obsolete. The Webb telescope in this single encounter redefined what it meant to explore space. It didn't just find an ancient galaxy, it uncovered a flaw in the way time and matter were thought to interact across cosmic distances. It presented an object that by all rights should have required twice the age of the universe to form, and yet it had formed, matured, and beamed its light across the void just a few 100 million years after the Big Bang. Every calculation, every model, every elegant equation that had guided astronomy for decades was suddenly up for review as theory struggled to keep pace with observations. Some scientists began to look beyond conventional cosmology. Could this galaxy be evidence of a previous universe reborn in a cosmic cycle? Was it a remnant from a pre-Big Bang epoch preserved through unknown physics? Others speculated that we might be witnessing the effects of higher dimensional phenomena where structures from other realms imprint themselves onto our own spatium. These ideas, while provocative, were no longer fringe musings but necessary avenues of inquiry in the face of evidence that refused to be ignored. This impossible encounter was more than a data point, it was a call to rethink the deepest assumptions about the cosmos. It challenged the notion that the universe has a singular, predictable history and hinted at a reality where time flows differently, where galaxies are forged in the crucibles of unknown laws, and where the universe itself might be far older, stranger, and more complex than previously dreamed. The James Webb Space Telescope had done what no other instrument had managed before, not just to observe the universe, but to reveal how little we truly know about it. With each passing day, more light from this impossible galaxy reached Webb's instruments, bringing with it more questions than answers. Researchers pored over the data, recalibrating models, cross-referencing observations, and searching for a framework that could contain this revelation. But for now, the encounter remained a puzzle carved into the fabric of the cosmos, a reminder that even in the age of unprecedented technological prowess, the universe still holds secrets that dwarf the scope of human imagination. This singular discovery, born from photons that journeyed across time itself, marked a new epoch in astronomy. It was a moment when the veil lifted, however briefly, and behind it was not a clearer picture of the cosmos, but a mirror reflecting the infinite depth of our own ignorance. The James Webb Space Telescope, designed to illuminate the past, instead cast a shadow on everything thought to be known, revealing that in the grand expanse of deep space, the truly impossible does not mean the untrue, it means the undiscovered. The moment the James Webb Space Telescope (JWS) recorded its impossible encounter in deep space, a new chapter in observational astronomy began, one that quickly diverged from the comfortable script written over decades of cosmic research. As more data poured in, revealing further layers of strange surrounding the anomaly, researchers realized that what had initially seemed like a singular discovery was merely the first crack in a vast wall of unexamined assumptions. This anomaly was not a fleeting curiosity, it was the ignition of a scientific revolution. What made this discovery all the more jarring was the symmetry and internal consistency of the object. Its rotational dynamics were not only consistent with gravitational binding, but also unusually stable, especially for such an early epoch in the universe's lifespan. The spin rate of the galaxy, when analyzed in relation to its mass distribution, suggested a level of galactic maturity that would typically requires several billion years of mergers, interactions, and internal feedback processes. Yet here was a galactic system that had achieved all that complexity within mere hundreds of millions of years after the Big Bang. The stability implied a deeper, perhaps pre-established coherence in the physics of the universe that defied conventional causality. As scientists drilled deeper into the object's motion and gravitational lensing effects, more peculiarities surfaced. The gravitational field surrounding this galaxy was disproportionately intense compared to its visible mass. Normally, this discrepancy is chalked up to dark matter, the unseen scaffolding that binds galaxies together, but the distribution of gravitational influence in this case didn't match expected dark matter halos. It seemed more concentrated and orderly, unlike the typically diffuse amorphous halos seen around contemporary galaxies. This prompted questions about whether we were seeing a new type of gravitational interaction, possibly an unknown state of matter, or even a modified gravity regime that only becomes apparent at certain scales or energy thresholds. Further complicating the picture was the galaxy's relative isolation. In the early universe, galaxies often formed in dense clusters or proto-superclusters, their formation influenced by shared gravitational fields and cosmic filaments. Yet this galaxy sat alone, untethered from the usual web of galactic kin. The vacuum around it was unusually clean for its age. There was a noticeable absence of the typical signs of past collisions, such as stellar trails or disrupted arms. This isolation was perplexing. It suggested either a very different formation process or some kind of hidden mechanism that protected this system from the usual cosmic rough and tumble. The idea that such an organized structure could evolve in a pristine pocket of the early universe implied that the large-scale structure of the cosmos might be more variable and less deterministic than previously assumed. The geometry of the galaxy was equally surprising. The shape was not just a generic spiral, it bore characteristics of a barred spiral galaxy with a prominent central bar and distinct star-forming arms extending outward. Barred spirals typically evolve from normal spiral galaxies through complex gravitational interactions and secular evolution over billions of years. The presence of such architecture in a supposedly primordial object raised the question: had the universe developed a fast-track mechanism for morphological evolution, or was this galaxy a witness to laws of galactic formation that had only now come to light? The colors emitted by the galaxy also confounded expectations. Its light spectrum was not the typical red tinge hue expected from objects at high redshift. Instead, it showed gradients of ultraviolet and near-infrared light that seemed to oscillate or fluctuate when observed over time. These color shifts could not be attributed solely to known redshift patterns or Doppler effects. Some researchers speculated that this oscillating color might hint at quantum-scale interference patterns magnified to galactic proportions, an idea that bordered on science fiction but could not be immediately dismissed given the hard data. It was even proposed that what Webb saw might not be a singular galaxy at all, but a superimposed echo of multiple galaxies entangled through gravitational lensing, or some exotic form of spatial distortion arising from unknown relativistic effects. In the wake of this encounter, theorists began Combing through earlier satellite data wondering if similar objects have been overlooked by instruments like Hubble or Spitzer due to their lower sensitivity in the infrared spectrum, retrospective analyses of ambiguous signals and faint anomalies revealed subtle hints that such galaxies may have appeared before quietly, faintly, almost invisibly, but have been dismissed due to noise thresholds or confirmation bias toward known models. The implication was chilling. We may have been looking at the impossible all along, blinded by the expectations built into our algorithms and methodologies. Perhaps most fascinating was the relationship between the galaxy and time itself. Some models began entertaining the concept of time behaving differently in different regions of the universe, possibly due to variations in the energy density of space. The notion of cosmic time bubbles emerged, zones where time could expand or contract at different rates depending on the local curvature of space-time. Influenced by factors still unknown under this framework, the impossible galaxy may not have formed quickly in a young universe, but rather evolved at a normal pace inside a region where time flowed more slowly compared to the surrounding cosmos. This would create the illusion of accelerated evolution when viewed from our frame of reference. While deeply speculative, the concept provided a tantalizing bridge between quantum mechanics, general relativity, and cosmology. Another radical interpretation involved the holographic principle, the idea that the universe we observe is a three-dimensional projection of information encoded on a distant two-dimensional surface. If true, it would imply that the distant galaxy was not so much a physical object as it was a rendered representation of deeper cosmic data. This idea borrowed from string theory and black hole thermodynamics suggested that the encounter with this galaxy was actually an encounter with the underlying code of reality itself. It opened the door to experimental metaphysics. Maybe Webb had caught a glitch in the cosmic projection, a fragment of code leaking through the fabric of the observable universe. Some astrophysicists also turned to the idea of early universe inflation anomalies. Inflation theory posits that the universe underwent a rapid expansion immediately after the Big Bang, but some hypothesize that certain pockets might have inflated differently, leading to vastly different local conditions. If this galaxy had formed in a slower inflating bubble, it might have had conditions more favorable to rapid development. In this view, our universe is a mosaic of inflationary patches, each with its own timeline and set of physical laws, some conducive to rapid galactic maturity, others following the more familiar slow-paced script. Meanwhile, high-resolution gravitational wave models were integrated into the analysis. Though gravitational wave detection at such a distance is still in the realm of theoretical ambition, simulations were run to estimate what kind of gravitational signatures a galaxy like this would have left if it had interacted with its surroundings. The outputs suggested ripple patterns inconsistent with standard black hole or neutron star mergers, leading to the bold proposal that this object may have originated through an entirely different gravitational collapse mechanism. Perhaps the collapse of an exotic form of matter, or even a relic cosmic string from the early universe. As Webb continued its mission, data began to show signs that this was not an isolated temporal outlier but one of many nodes in a deeper pattern. A second, then a third, and eventually a half-dozen galaxies were found in similar cosmic conditions, each bending the rules of time, mass, light, and structure. These weren't identical clones, but each displayed some form of developmental anomaly, unusually rich in metals, disproportionately massive, or morphologically too complex for their age. The statistical impossibility of so many coincidences eroded the argument for mere observational errors or instrument glitches. A new cosmological model would be required, one that didn't just tweak parameters but rewrote the code. In tandem with these discoveries, the field of exoplanet research also found itself invigorated. If galaxies were evolving faster, then perhaps planets, too, had an earlier start. The potential that some of these systems could host long-dead civilizations or ancient biospheres wasn't pure speculation anymore. It became a point of legitimate inquiry. Signals previously dismissed as statistical noise or instrumental interference were re-examined under the light of Webb's breakthrough. Astrobiology was no longer just a field about life that might exist now. It expanded to include the possibility of life that had risen and vanished before Earth had even cooled. The role of black holes in this narrative also became more central. A new hypothesis emerged suggesting that early black holes may have functioned not just as galactic anchors, but as cosmological accelerators, regions where matter, energy, and even information could be compressed and transformed in ways yet to be modeled. If some primordial black holes had properties beyond those currently known, if they could spawn stars, seed galaxies, or even generate localized expansions of space, they might be the architects of these impossibly early galaxies. Cross-disciplinary collaboration erupted. Quantum physicists, data scientists, and philosophers of science found common ground in the need to interpret a universe that no longer conformed to linear extrapolations of the past. Artificial intelligence tools were employed to sift through terabytes of observational data, looking for hidden correlations between anomalies. Machine learning algorithms began detecting subtle patterns that hinted at a deeper cosmic structure, a fractal rhythm or underlying symphony of form and energy playing out over scales far beyond human comprehension. Theoretical cosmology, once a field guided largely by elegant mathematics and philosophical speculation, now had a rich vein of raw, undeniable data to dig through. The impossible galaxy became a cornerstone of what some began to call cosmic archaeology, the study not of what was simply far away, but what was deeply buried in the substrate of space-time itself. The universe, it seemed, had kept secrets not just in distance but in the complexity of its unfolding. The Webb telescope's impossible encounter had not just shifted the scientific consensus, it had shattered the illusion that the cosmos was fully charted. It reminded humanity that the universe is not obligated to be comprehensible, that the maps drawn by even our most advanced tools may still be inadequate for the terrain ahead. And as scientists worldwide continue to peer deeper into the vast reaches of space, the legacy of that discovery grows. It lives not just in academic papers and data sets, but in the minds of those who now view the universe not as a solved puzzle, but as a living, breathing mystery. In this moment, space is no longer the final frontier. It is the beginning of something even more profound. Not merely a void to be crossed or a domain to be explored, but a vast, unknowable structure that reflects back the limits of human understanding. The James Webb Space Telescope, through a single improbable observation, has rekindled the essence of science, the embrace of uncertainty and the thrill of the unknown. And that, more than any measurement or equation, may be its greatest contribution to the story of the stars. The deeper the James Webb Space Telescope explored into the early universe, the more it unveiled a domain that seemed alien not merely in terms of distance or scale, but in the very logic that governed it. Following the initial impossible encounter with the mature, structured galaxy from the cosmic dawn, the telescope began to observe peculiarities that expanded far beyond isolated anomalies. These weren't just outliers against the backdrop of accepted theory. They formed a constellation of contradictions that collectively pointed to an entirely unrecognized layer of cosmological architecture. New targets selected to investigate the same epoch as the original discovery began yielding results that were progressively more unexplainable. For instance, several galaxies exhibited not just chemical richness, but compositional anomalies, ratios of elements that defied known stellar nucleosynthesis patterns. Instead of the expected proportions dominated by hydrogen and helium, there were galaxies with abundant signatures of elements like magnesium, silicon, and even platinum. These were not just present in trace amounts. In some cases, they appeared in concentrations suggestive of intense stellar recycling cycles. But such cycles required time that simply hadn't passed yet. This pointed to a hidden mechanism, perhaps a hyper-efficient stellar generation system, or even a non-stellar origin of heavy elements. One radical hypothesis posited the existence of primordial particle interactions that could result in direct element synthesis without the need for stellar fusion. This idea, if validated, would dismantle the notion that stars are the exclusive forges of the periodic table. It suggested that the early universe could host chemistry as complex as our solar neighborhood, not through the familiar pathway of stellar evolution, but via physics that had not yet been observed or understood. Meanwhile, attention turned to the spatial distribution of these anomalous galaxies. Unlike the generally uniform structure predicted by inflation and the cosmic microwave background, these regions seemed spatially clustered in a loosely coherent pattern, an invisible thread of unusual cosmic geography. The shape and spread of these clusters suggested an unknown influence shaping them, a cosmic architect sculpting matter and energy in precise, non-random ways. This led to renewed interest in cosmic topology, the study of the universe's large-scale shape and whether high-dimensional influences could be dictating local matter configurations. The suggestion that geometry itself might be more dynamic and locally variable than previously thought raised new interpretations of general relativity. Certain teams began to theorize that spacetime might possess localized properties akin to phase transitions in condensed matter physics. In essence, the universe might include pockets where the fabric of reality underwent a shift, subtle changes in the curvature and connectivity of space and time that allowed for faster-than-expected structural development. These cosmic phase pockets might explain not only anomalous galaxy formation, but also unexpected gravitational behaviors in early structures. Intriguingly, further data revealed a specific class of galaxies exhibiting a form of synchronized starburst activity. Their internal structures pulsed with waves of star formation that swept across the arms like a coordinated signal. This pattern could not be explained by internal dynamics alone. The coherence hinted at an external influence. The notion that intergalactic communication or causality could exist at such early times began to gain traction. One proposal involved a kind of background quantum field, perhaps a relic from the universe's first microseconds, oscillating across vast distances and triggering galaxy-wide reactions. This field would act as a metronome, regulating processes in areas that should otherwise be causally disconnected. While some looked outward, others turned inward, toward the telescope itself. Was it possible that the Webb telescope sensors were sensitive to phenomena never before observable, even accidentally capturing phenomena outside the electromagnetic spectrum? Although designed primarily for infrared imaging, Webb's unprecedented sensitivity and stability could make it a tool for detecting faint interactions between particles, or even hints of exotic quantum fields. Some even speculated whether Webb was perceiving not just matter and light, but imprints left behind by previous cosmic cycles, an idea steeped in the controversial framework of conformal cyclic cosmology, which postulates that the universe undergoes infinite expansionary epochs, each beginning anew but retaining subtle echoes of the last. This echoed in another strange detail: background fluctuations in regions devoid of visible galaxies. In multiple cases, areas of deep space recorded odd low-level energy signatures that did not correspond to any known background radiation. These energy fluctuations were too structured to be noise, but too faint and disorganized to represent traditional matter. The patterns vaguely resembled the theoretical profiles of decaying vacuum energy or the remnants of false vacuum states from inflation theory. If confirmed, this could imply that our universe was still transitioning between energy states, an incomplete universe in the process of settling into its physical laws. Another axis of investigation came from polarization analysis. Webb's polarimetry instruments were designed to analyze the orientation of light waves, and in some of these galaxies, the polarized light was inconsistent with scattering from dust or magnetic fields. Instead, the light appeared twisted in a pattern consistent with interaction from chiral particles that behave differently depending on their orientation. This brought attention to the possibility of handedness in the early universe, a bias in symmetry that might hint at why matter dominates over antimatter. If these interactions were prevalent in the early universe, they could have had cascading effects on the formation of galaxies, stars, and perhaps even life itself. Astrobiologists were particularly intrigued by this revelation. A chiral bias in cosmic formation processes could imply that the basic ingredients for life, amino acids, sugars, nucleotides, might have originated with a universal asymmetry favoring one orientation over another. That would mean life, at least in its chemical foundation, might not be as arbitrary or emergent as once thought. It might be written into the universe's architecture from the very beginning. If Webb's data pointed toward this kind of bias embedded at a galactic scale, it could have staggering implications for the frequency and form of life elsewhere in the cosmos. While most analysis remained grounded in hard data, more philosophical and theoretical inquiries bloomed. One line of thought proposed that what Webb had discovered wasn't just a distant object, but an observational artifact caused by our own position in the universe? What if the laws we observe are shaped by the curvature and expansion of space specifically at our vantage point, creating illusions of anomaly when viewing across cosmic distances? This concept, rooted in anthropic reasoning, suggested that our understanding of physical constants and cosmic evolution might be non-universal, local phenomena mistaken for global truths. If you like this video, please give it a like and subscribe to our channel. Also leave your comments below and tell us what are your thoughts on JWST's impossible deep space.